Well, a warm welcome to everybody. Thank you for being here. Welcome in. Great choice that you're here. Get yourself ready with a notebook. Grab a pencil or pen. Whichever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. Today we have a problem from the 2007 AP Calculus BC exam. Now, I do know some people in my personal life who took the 2007 AP exam. It was a while ago. It was some of my older brother's friends. And I'm not sure if they were in BC during 2007. They might have just been in AB, so it's possible they didn't get this question either. Just goes to show you how long people have been doing AP Calculus. For decades. Okay, in any event, this is a BC question. It involves polar curves and calculus with polar graphs. So if you're in AB, sorry to say, you are not welcome here. I'm just kidding. You're absolutely welcome here. But you probably won't really understand what's going on. So you can be a keen observer if you'd like, but for the rest of y'all in BC, go ahead and give yourself about 12 to 15 minutes to do this problem. Now, I'm not convinced this is a calculator exclusive problem. Seems like it can be done without a calculator since these angles are nice and there's not like some crazy ln or something really weird thrown in there. It's pretty basic. 3 plus 2 cosine theta and r equals 2. Those are totally reasonable. Then when you're ready, after you've attempted the problem, come on back. See how we did it here. All right. So let's get started with interpreting the problem. We have the graphs of these polar curves, r equals 2. That would be this circle centered at the origin, the radius of 2. And r equals 3 plus 2 cosine theta, which is a limacon. Okay. Limacon with a little dimple. And that is this one here. So you can see that they've kind of separated and shaded a region. And it also tells us where the curves intersect, which is nice. This is at theta equals 2 pi over 3, and this is at theta equals 4 pi over 3. That's for convenience, right? Very useful to tell us that. Okay, well, let's get started with part A. Part A is let R be the region that is inside the graph of r equals 2 and also inside the graph of r equals 3 plus 2 cosine theta as shaded. So we need to parse this out because we need to find the area of R. So what we're going to notice is we're going to notice that up to the angle of, maybe I should use a different color, up to the angle of 2 pi over 3, the shaded region is completely contained by the circle r equals 2. And then again, from 4 pi over 3 to 2 pi, again, the region is contained or bounded simply by the circle equation, okay? So we're going to say this purple segment, that area, is equal to 2, because of the symmetry across the polar axis, is equal to 2 times, well, 1/2, since that's in the area formula for an integral. Let's write out the area formula really quickly. All right, we say that the area is 1/2 integral from angle alpha to angle beta of r of theta d theta. So this is going to be 2 times 1/2 integral from 0 to 2 pi over 3 of r squared, which is just 2, which is 4. All right, so this is just going to be integral from 0 to 2 pi over 3 of 4 d theta, which is simply going to be 8 pi over 3. Now let's talk about this other portion, a little bit more interesting, this other portion which is only bounded by the limacon. And that's also symmetric, so what we can do here is we can go from, it's going to be 2 of them, maybe I won't use red, kind of an abrasive color. That's 2 of them times 1/2. Integral from 2 pi over 3 to pi of 3 plus 2 cos theta squared. So I guess you could probably use a calculator for this part, but let's just FOIL it all out. If you're quick, it really shouldn't matter that much. Plus 4 cos squared theta d theta. So this is going to turn into, you might be familiar with this use of the double angle formula. It's going to be 2, so this is going to be from 2 pi over 3 to pi of 11 plus 12 cos theta plus 2 cos 2 theta. It's really nice to have that 2 in front. You'll see why when we integrate. This is going to be 11 theta plus 12 sine theta, very doable, plus sine of 2 theta, because the derivative of that would give us that extra multiple of 2. It's kind of nice. And we're going to evaluate this from 2 pi on 3 to pi. So let's plug in pi, and everything's really nice here because 11 pi is the only thing that remains, plus 0, minus 22 pi on 3, plus, let's see, sine of 2 pi on 3 is rad 3 over 2. So we'll have 12 rad 3 over 2. And then sine of 2 times 2 pi over 3 is sine of 4 pi over 3. That's a negative rad 3 over 2. So all of this, since this is 33 pi over 3, and let's see, distribute those negatives, so this is going to turn into plus rad 3 over 2, but minus 12 rad 3 over 2, for a total of minus 11 rad 3 over 2. So we get 11 pi over 3 minus 11 rad 3 over 2. Okay. We're going to combine those together, right? The total is simply going to be, let's see, we have 11 pi over 3 and 8 pi over 3 for a total of 19 pi over 3 minus 11 rad 3 over 2. Now let's see, some kind of quickish math. So that's going to be, 9, 5, 3, 6. What's 19 pi over 3? Goodness. Well, I shouldn't approximate that much. Pi is 3.1416-ish. So if I divide that by 3, I'm already kind of rounding a bit sloppily, I'll admit. 0.46, let's say. And if we're multiplying that by 19, we can just multiply it by 2, and then multiply it by 10, and then subtract. So we'll have 19.88-ish, and then we're subtracting that. Yeah, if I had to guess, I'd say about 10.33-ish. You could totally use a calculator for that. I think it probably takes a little bit longer than most students can do by hand, so feel free to use a calculator for that part. Okay, part B. A particle moving with non-zero velocity, okay, it's good to know, along the polar curve given by this, okay, has a position. So it's basically parametric because we're using r equals 3 plus 2 cos theta, but we have the position according to, x of t, y of t. Find the value of dr dt at theta equals pi over 3. Well, that's really easy because dr dt apparently also equals dr d theta. So we can just say, let's move that here. Dr dt evaluated at theta equals pi over 3 just equals dr d theta with, again, evaluated at theta equals pi over 3. Well, the derivative the derivative of r with respect to theta is simply going to be negative 2 sine theta. So if we evaluate that at theta equals pi on 3, we're just going to get negative 2 times sine pi over 3. So we're going to get negative rad 3, which is approximately negative 1.732. Now, I know this from experience. You could use a calculator if you want to, but I've done so much trigonometry that it's kind of useful to remember what the decimals are for, like, rad 3 over 2 and root 2 over 2. Those are kind of useful. Therefore, if you multiply it by 2, you get root 3. If you multiply rad 2 over 2 by 2, you get root 2. No surprise there. So that was strangely easy. I think this could be done by hand because that was so fast. That took no time. All right, part C. For the particle described, find the value of dy dt. And it tells us that dy dt is dy d theta. So, it also says to interpret your answer in terms of motion of the particle. So we need to do that. If dr d theta is negative, what does r stands for? R is distance from origin. Therefore, let's move this somewhere else and make it a little bit smaller in font. So, dr d theta let's keep filling in here, tells us the particle moves away from the origin of 1.732 per unit time. Okay, so that's the interpretation. That is also important. That gives us a point for sure. If it says interpret your answer in terms of motion of the particle, that's worth a point, maybe even 2. All right, part C. For the particle described, dy dt equals dy d theta. So find dy dt. Should put that in red. At theta equals pi over 3. And again, interpret your answer in terms of motion of the particle. Now the y value is like, the y distance. So dy d theta tells us if it's going up like that or down like that. So let's take a look. What is the y value? Remember that y of t equals r times sine of theta, which means 3 plus... Oh, am I looking at the wrong problem? No, that's correct. 3 plus 2 cos theta times sine theta. So that means that dy dt, which equals dy d theta, according to them, is going to be a product. How do we do derivative of a product? We take the derivative of the first thing times the second, plus leave the first thing alone times the derivative of the second. And this is very easy to do. This is just negative 2 sine theta. We already kind of did that part. And leave the sine theta alone, so we have negative 2 sine squared. And then we're going to leave 3 plus 2 cos theta alone, and we're going to multiply by the derivative of sine theta, which is cos theta. We don't have to simplify this stuff. We just have to plug in. We can do some nice little trick here, by the way. So this is equal to 3 plus 2 times cos squared minus sine squared. You don't have to do simplification, but guess what? This turns into cosine of 2 theta, which is really convenient. So if we want to plug in theta equals pi on 3, that means we're going to get 3 plus 2 cos of 2 pi on 3. Cosine of 2 pi on 3 is negative 1/2. Let's put that in parentheses so it doesn't look like 2.5. 3 minus 1, so that's just 2. That means that y is going up. It's increasing, but we don't know where it is technically. Let's see where it actually is at pi over 3. Let's get y of pi over 3. That's just going to be 3 plus 2 cosine of pi over 3. And then all of that is times sine of pi over 3. Let's see if the y value is negative or positive. We know that it's going up, but we don't know if it's going towards the x-axis because it's below, or if it's going away from the x-axis because it's already above. So this is going to be 3 plus, again, cosine pi over 3 is 1/2, so this is 3 plus 2 times half, which is 3 plus 1, times rad 3 over 2, which is going to be 2 rad 3. So we have a positive y value, and we have a positive derivative. So our interpretation is that the y value is already above the x-axis, and the derivative is positive, meaning that the particle is moving away from the x-axis at this time. Okay, and that gives a point as well. I don't think this should have been done with a calculator. If you need a calculator, that's fine. I'm not going to shame you about it. But as you can see, these are skills which you did learn in this year of Calculus BC. So it's not unreasonable to expect you to be able to do these things. Now, do you need to get a decimal and round it like this? No. You could totally leave the answer like this, and you would probably still get just as much credit as I did doing this. In fact, I might lose points if this approximation is wrong. So just keep that in mind. The exact answer is always true, more true than the decimal representation. But other than that, we really got to see what happens when we have two polar curves and an area that's bounded by them, but they sort of switch who's the boundary, right? It sort of switches between this circle from 0 to 2 pi over 3. Thankfully, they gave us that value. If they didn't give us that value, I can understand using a calculator to try to solve that really quickly. But even then, it's pretty easy to set them equal to each other and solve. You just get that cosine theta has to equal -1/2. So that has to be at 2 pi over 3 and 4 pi over 3 anyways. See how all of these trigonometry skills just come and play in these polar functions? And then we have to sort of trade off who's the boundary now, once we get to 2 pi over 3, for this little wedge, this little dimpled portion is being bounded only by the limos. Okay, so could be done with Desmos. Doesn't need to be done with Desmos. It's the moral of the story. I encourage you to do whatever you can without a calculator first. Get as many points as you can, and then at the very end, go ahead and use a calculator if you need to. Don't forget the interpretations. These are strong points that you should be earning, right? But I think that's enough blab out of me, so I will leave this until we see you guys next time in the void.